Alrighty then. Oh, right before it starts to get good. Okay, let's begin. Good morning, everybody. Very small everybody, but it still counts. Okay. We've got some sweet algebra action for today. Let's start by going over answers from yesterday with the roots of rational numbers. So here on my screen are my answer. Let me zoom in a little bit more. That's probably better. Okay. So most of these are pretty straightforward. What is the square root or possibly cubed or fifth root? Oh, fifth root. This was a good one. Of some of these numbers, and then use your exponent properties to work out, okay, how many powers of p do I need that if I then raise it to the fifth power, I will get 10. It's just division. 10 divided by 5 is 2. Right? It's exponent properties all over again. So take advantage of that where you can. No need to overthink and rethink and things. The only part that I would say throws you off is the presence of negative signs at any point. And so a lot of these they're asking for, what is the negative root of these numbers? Well, the negative root would itself be a negative value there. Okay? And here, can I have a cube root of a negative value? Yes, you can. An odd power of a negative is still negative. Even power, it would not work out, and that's where you get into trouble, like with 17. I actually had to add this one in myself because the book is all like, oh no, it's not a real number. I'm like, yeah, but we totally did complex numbers already book. So yeah, the square root of a negative gives you the I, and then that negative in front says, give me the negative root. So it's still a negative 0.6i. Okay. And then when they ask for positive and negative here, sometimes that means they want both of them. So you got to list the positive and the negative. That's it. Oh, I missed. 12 there should have a negative sign. Yeah. No, 12 does not. Oh, I'm sorry. Nix that, because it's a negative of a negative, right? So the cube root of the negative 27 would be negative 3, but they want the opposite of that. That's why I didn't have that there. Okay. Thought I made a mistake, and then I made a mistake in mistaking. Okay, and these last couple introduce a rather interesting idea. Is it critical that you have the absolute values here? I would say not really, as far as what the root is, but it does get into our definitions of absolute value and how we actually compute that. Like, if you use the absolute value function on a calculator, what is the calculator actually doing? Most of the time, it is doing this right here. This is the poor man's absolute value, if you will, right? Is to take a quantity, square it, and then square root it. Because as we know, even if it was negative, when you square something, it's guaranteed positive. And then I square root it to get back down to the original value. And because I don't have the negative in front, I'm always taking, by default, the positive root. So that, in a sense, is the same process as stating take absolute value of 3x minus 1. And you get the same result here for 24 after you factor this. Okay. So with that, any questions from the first page?
We were just doing the odd numbers, right?
Were you? Yeah. Oh, so you didn't get 22 and 24. All right. Well,
Yeah, on the description it said odd exercises.
yeah, that's true. I put them all on
And
here,
then
but
and then
forgot
for
about that.
number three and for number three, wouldn't it be 12p cubed? And the same.
P cubed. Half of 6 is 3. You are absolutely correct. Thank you. What I get for trying to read small print sideways when copying these down. All right, any others? I forgot you only did odds. Oh, that means you missed out on 22 and 24. What a bummer. Okay, well, then let's go on to the next page. The calculator approximations. And we are rounding to 3 decimal places, so yours should be pretty exact here, unless again I miswrote something. Right, and then you doing only odds, you would have only done number 19 there. And that's just here's the formula, put the numbers in. All right, any questions on this page? No? Then let's go on to the next section for today. 5 points. Why am I way down here? Radical expressions, which is it's more of the same, really. They kind of already mixed it in. I'm really upset with this book. They said the other one was roots of numbers, but they threw variables in there. And now this one's like, oh, it's expressions with more variables. Like exactly the same. But what we've done here is we've introduced two properties that you may already be familiar with. The product property and the quotient property, exactly like we had on exponents. Right, so I would just zoom in on this bit here. This is the best summary, I would say. You have a root of two things being multiplied. You can instead have two roots being multiplied, right? You can separate those out individually. There is the fact that n being even just makes that extra catch of, well, okay, they both have to be non-negative. Adds extra words there, but this picture will show you all you need to know. I can always split off anything and take that root separately. Okay? And I actually like their little steps here, 1, 2, 3. I wouldn't necessarily write them all out, but certainly thinking through this, yes. Step 1, always factor stuff. Okay? And if you're dealing with a square root, then you're going to try to find squares. If you're doing a cube root, try to find cubes, right? And use that product property to find anything that you can square. Take that out, set it aside, simplify, right? That is the process. You split the factors. Whatever you can take out in square root, you do, and you leave the rest inside the radical. Right? And same for quotient property. Right here, if you are taking the root of things that are being divided, you could instead divide two things that are being taken root. So long as, of course, b is not 0, right? I always have to add that in there, but like as if we would stumble across, if you see dividing by 0, you stop and do nothing anyways. All right, so let's take a look at these examples then. Simplify all that. Well, it's the cube root, so I'm looking for triples, right? So negative, I can do that, make sure that's a negative number. Do I have one number that multiplied by itself 3 times gives me 16? No. But, as they've done here, I can treat 16 as 2 times 8. And 8 is 2 cubed. So the negative 2 cubed gives me 8, and I'm left with an extra 2 there. So this guy gets to go outside. Negative 2. In front, the extra 2 stays inside. Okay? And then it's a matter of splitting these up. Okay, well, I can take out 3 of the 5 a's. So treat that as a cubed times a squared. Again, this is probably, I would not be writing this down. I would just be working through this as I go. What can I do with the number? Put that in front. What can I do with a's? I can take out 3 of them. And when you do so, it drops the 3 and 1 goes in front. You leave 2 inside. And b, I can take 3 of them out. And then I'm left with b to the 4th. I can take 3 out again, so I do that twice. Or you can think of it as b squared cubed. Right? So the b squared gets to come out front. And you leave the extra b inside there. And then for division, quotient property, right? You're basically turning this, right, all one big divide. Ooh, okay, well, I can't simplify this fraction inside here. I can't, 8 over 45 does not reduce down, okay? So instead, let's try to take the square root of pieces individually. Can we square root anything up here? Yes, we can. I can split 8x cubed. I can treat that as 2x squared times 2x. Okay, so we take the x out, and we take a 2 out at least. We can at least do that much, and that simplifies. Right? Then we separate them as such, and pull that out. We get the 2x times root 2x. Same with the denominator. We treat 45 as 3 squared times 5. And so the 3 can come out. I can get 2 y's out of there. One of them stays in. And all that's left is just deal with that little rationalize the denominator. It's not as big of a feature as it once was, but we'll go ahead and follow through with that. It does look a little bit nicer, I would say. Now we only have one radical to deal with. Right, so multiplied by that radical, same on top and the bottom, so that these square roots get squared away. And you're left with 2 times absolute value of x. Why is it absolute value? Well, because we squared it and then square rooted it, right? So it becomes the absolute value of x. And that's just a reminder there that, hey, whatever value of x you put here should still give a positive result, even if we no longer have that squaring and square root represented there. Okay, any questions there? I think this is the most straightforward one. In fact, there's only 6 exercises to go along with this page. So instead, let's turn our attention to the second page. There's a little bit more involved. Operations with radicals. Okay, multiplying and dividing is easy mode. But as usual, when you start trying to add and subtract funky stuff together, oh, now you gotta deal with it a little more involved. Okay. So here's what I would do. I've summarized both of these examples here into a similar, like, 3-step process. Factor, simplify, and combine. Okay? You follow that, and you'll be able to work through any of these, no matter how big and ugly they get. Start by finding your factors. Okay? Just factor tree everything under a radical, if necessary. Okay? Factor out the 50, find pairs, pull them out, and that's part of simplifying, right? Once you have all your factors of everything, once you know that 50 is in fact 5 squared times 2, and 500 is 10 squared times 5, right? Now I can simplify by taking the square root of 5 squared. Pull that 5 out in front. Okay, so I get 2 stays there, 5 squared becomes just 5 in front, and I still have 2 underneath the radical here. Right? And then keep simplifying as far as you can go. 2 times 5 is 10. Okay, so now I have 10 root 2's. Right? When we do the same thing, we get 40 root 5's minus 30 root 5's. And then just combine like terms. Treat your simplified radicals as variables. Okay? They are separate terms, so I cannot combine so many root 2's with so many root 5's, but I can combine 40 root 5's with negative 30 root 5's and get a net result of 10 root 5's. That does work. Okay? Here with the multiplying, I kind of have to, I'm multiplying two binomials, so always start with distribution. So I guess instead of factor, it's distribute. It's kind of the opposite there. But you're still then going to go ahead and simplify and start combining like terms. Division is the trickiest. Division is where we got to bring in something new here. And that is you got to get rid of this thing in the denominator, but it's being added to something else. I can't just multiply by square root 5 over square root 5. So I got to get really fancy. Right? We're still going to multiply by a foo here, fancy form of 1, except our fancy form of 1, that's this guy right here, is the conjugate. Okay? Notice that the 3 is the same, the square root 5 is the same. The thing that is different is the sign. Take that exact same denominator, switch the sign, and multiply by that on the top and the bottom. Because look what happens. You get this beautiful thing. 3 times 3 is 3 squared. Beautiful. Square root of 5 times square root of 5 is square root of 5 squared, which is just 5. And then you have the crossover pieces, right? 3 times negative square root of 5 plus 3 times positive square root of 5. That's going to give you a positive and negative version that delete each other and 0 middle term, right? It's exploiting that difference of squares factorization. Okay? Those special products can come in handy even when we're not just factoring. They come up again in dealing with this kind of garbage. All right, math, you thought you were so tricky throwing square roots at us. We got this covered. Any questions on multiplying, adding, subtracting, dividing, radical expressions? Hearing none, then I leave you with those 6 exercises up there and these 12 exercises down here. Okay, whole thing, you get to do them all today. There's not that many, and with that I will end the stream there.